So now we're going to take a look at increasingly more complex circuits. The big distinction between kind of the introductory circuits, which is everything before this point, and what we're going to do now is the following. Everything that we've done up to this point has been solving one simple circuit with one resistor and applying Ohm's law, delta V equals IR, to the whole thing. Now, we've been playing a little fast and loose because it's technically the resistance of this resistor, the potential difference of this battery, and then the current that is going through the entire circuit. So the current coming out of the battery. What we're going to do now is we're going to see how we can start to take apart and learn more about what's going on in even the most complex circuits. Now, we started to work with complex circuits. We had really complex ones, say something like this, that would then split into this. It would have another one over here with these, and then some over here with these. That's a fairly complex circuit, at least by our standards. But what we've done up to this point is we've used equivalent resistance to turn it back into this circuit. What we want to do now is we want to be able to know what's going on in each of these individual resistors. And that was something that we didn't do before because we were too busy combining them to turn them back into the simple total circuit that we've been looking at. Now we're going to start exploring that, which means we need to get some more information than what we currently have. All right. So here's what we're going to do. We're going to do a little bit of exploration with some of the lab equipment I've got and one of my meters here. So give me just a moment. I'm going to take this off. Here we go. Pull these apart. Here's my power supply. I'm going to set it to 3 volts. It is currently set to 3 volts. And here's what I'm going to do. I'm going to put one end here and one end over here. Okay? So basically what I've set up is the following. I've set up a relatively simple circuit that looks like this. Here's my battery. I've got it wired in. It goes into one resistor that then goes into another. We've got 2 of them in series. Great. So I could go through, I could do some stuff with this. In fact, I'll go ahead and mark it that we've got a 10 ohm resistor and a 10,000 ohm resistor. Man. And I've got them in series. Here's what we want to do. I would like to look at the electric potential differences, the voltages, if you will. And if I were to call this RA, this is resistor A, and this is resistor B, one of the things that I'd like to know is I'd like to start taking a look at some of our potential differences. Now, we've got a battery that will be set to 3 volts. That's our power supply here. One of the things I'm interested in is delta VA, the potential difference across A, and delta VB, the potential difference across B. Now, I'm going to bring this back to something that we had mentioned before, where potentials are a lot like heights. So I want you to imagine that the battery is basically lifting these charges up from 0 to 3 volts. That's kind of what batteries do. They lift things up so that they give them energy. And as the charges move through the circuit, they'll actually fall down some height. So let's take a look at what we can find here. I'm going to switch this over to 20 volts. That's the maximum that it'll read right now in this setting. I'm going to turn this on. I'm going to power up my circuit. And now this is set to be something called a voltmeter. And what I'm going to do is I'm going to measure the potential difference across these things. First and foremost, I'm going to check the potential difference across my battery. 2.97. So we're not exactly at 3. Like I said, these things do pretty well at maintaining themselves, but it's really hard to get exactly 3. So 2.97. That being said, we've got a total value of 2.97. We'll just call it 3. If I look at the potential difference across all of the resistors, they come up to 2.97. It's actually the same as what's supplied by the battery. We've been using that up to this point. But what I'd really like is not the potential difference across A and B. I want it across A. So I'm going to put it just on the ends of A. That's interesting. It may not be what you would expect. The potential across A is 0.01 volts. Okay, what about B? Let's see here. 2.97. And the total was about 2.97. It jumped up a little bit to 2.98. Huh. Maybe you can see a relationship in those numbers. Let's try something. Let's switch this out. So the 10K seemed to be the one that had a really big potential across it, whereas the 10 ohm didn't have much of one. That's another 10 ohm. Let's see. Why do I have so many 10 ohms? Here we go. Here's a 1000 ohm resistor. So instead of a 10 ohm, we're now bumping this up to a 1000. So if I were to draw this, it would look exactly like the one we just saw, except we've got a 1000 ohm and a 10,000 ohm resistor. Now, this is going to emphasize one thing that I mentioned before. If you change any part of the circuit, you may end up, and will likely end up, changing everything. Now, depending on what circuit we attach these things to, in fact, let's go ahead and double check that. This time, instead of just assuming it's going to be 3 volts, I'm actually going to take the measurement. It's 2.97. 2.97 volts. If you get a negative on this, you can actually just flip the leads. That technically said negative, but now that I flip these, I get positive 2.97. Okay, here's what I'm going to do. I'm going to take a look at the first resistor, resistor A in this case. That's the 1000 ohm. And this time, I'll try to put this where you all can see it, hopefully. We end up with 0.28. We have a different delta V, 0.28 volts. Okay, let's see what happened to the other one. It is not going to be 2.97 like we saw last time. It is instead 2.69, maybe about 2.7. Oops, I wrote that wrong. Not 0.269, 2.69. 2.69 volts. Okay. What happens if I had two 1000 ohm resistors? I'm going to take apart one of my other ones that I was going to check out here in a little bit. We'll put it back together. Two 1000 ohm resistors. Let's see what those come up with. So, trying this again. Here we go. I'm going to check the potential across the battery. 2.97 still. It's a regulated supply, so it's usually pretty good at maintaining a constant amount. 1.48. It's bouncing around a little bit. I'm not getting the best connection ever. 1.48. So we've got delta V equals 1.48 volts. And then the other one, this is with 1000 ohms for both of them. Let's see what we got. Oh, 1.48. Let's see what we can get from this. We're noticing something interesting about this. Let's see what we come up with. All right, in each of these cases, the total that's supplied by the battery is about 2.97. So let's take a look here. 2.97, maybe 2.98. Well, 2.97, that's pretty much the entire battery, and then we've got almost none in the 10 ohm. For whatever reason. We have a huge drop along the 10,000 ohm and almost no drop among the 10 ohm. Okay? But if I were to take 2.97, it's about the same as what I've got for the total there. In fact, I could add on this small amount and they'd come up to about the same. Let's see here. We had 2.97. What if I take 2.69 plus 0.28? 2.69 plus 0.28. I get 2.97. What about 1.48? It was kind of bouncing back between 1.48 and 1.49 when I could get a good measurement on it. When I add those together, that'd be 2.96. Noticing a trend. This is something that we're going to take a look at. Right now, it looks like, for whatever reason, when I measure the potential difference across each of these resistors, because they do have a potential difference, the battery or power supply is going to raise it up by a certain amount, in this case 3 volts or 2.97. And each of these resistors, the battery is going to give energy and the resistors are going to take it away. And how we represent that is by raising things up or lowering them down on a hill. The battery is going to push things uphill, giving them some energy. And as they fall through the resistors, falling downhill, they release that energy. Or through a light bulb, for instance. So we find that whatever is given by the battery, we end up losing some here, and we lose some here, and then we end up back at 0. We're discovering something very important and very useful for complex circuits. Let's take a look. This is just one example, and we kept doing a bunch of series ones. Let's see how this holds up on parallel. Right now, we've got an idea that whatever the potential difference is on these resistors, they have to add up to the total. So let's see what we come up with as we start looking at a more complex one. I'm going to restore this one back down here for one of the others. In fact, let's take a look at this one real quick. This is a series circuit now with 3 of them. Okay, so here's what I'm going to do. I'm going to snap this here. I'm going to snap this here. And I'm going to turn this on. We've got 3 volts. Drawing this out, I've got the following. I've got one here, and one here. We're going to say that this is 3 volts. It's probably about 2.97, but we'll check it when we get it. I'm going to go ahead and call it 3 volts. This one is a 100 ohm resistor. This one is a 10,000 ohm resistor. And this one is a 1,000 ohm resistor. Great. I'm going to turn this on. Here we go. I'm going to turn on my meter. Hopefully you all can see it. If not, I'll read it off to you. Let's check the 100 ohm resistor. Here's what I'm going to do. I'm going to put this across. 0.03. Delta V equals 0.03 volts. Sorry that it's kind of hard to read there. Not my best handwriting ever. All right, here we go. I'm going to check the next one. It's reading a negative, which means I'm actually hooking this up properly. But for our purposes, we're just going to treat the positive. I've got 2.68. So when you're working with this stuff in the lab, 2.68 volts for resistors. We're just going to take the positive number. All right. And then finally, I've got this one. I'm going to read the potential difference. We've got negative. I need to switch my leads, 0.26. If I switch my leads, I get the exact same thing. Oh, 0.27, but pretty much the same thing except positive. They should be the same thing. It's just rounding a little bit differently. 0.27 volts. That's what it seemed to be stabilized at. So we're going to go with that. I bet if I gave the other one the negative 0.26 a little bit longer, it would have gone up to negative 0.27. Great. I'm going to go ahead and turn this off. Let's see what we end. Oh, actually, let's double check what our total is just to be certain. 2.97. All right, so here we go. My total is 2.97 volts. That's what the battery is actually going to be giving. Let's see, if I take 0.03, I apologize, plus 2.68 plus 0.27, and I add those together, I find that the total around this for each of the resistors, if I add them all together, comes up to about 2.98 volts, which we saw that our supply was kind of bouncing back and forth between 2.97 and 2.98. All right, so even when we have 3 resistors, we seem to have stumbled across something. Whatever the potential difference is across each of the resistors has to add up to the total. Now, before you burn that into your memory, let's take a look at another type of circuit, the parallel one, because we've only looked at series. Maybe things are a little bit different. But right now, we've got a pretty good idea that there's a relationship between our potentials and our total potential difference for the battery. Oh, one other thing while we're here. You may have already noticed it. This is 100. It's the lowest resistance. It also has the lowest potential drop over it in this setup. That's not something that you want to remember all the way through, because that may not always prove true. But I will point it out. You may have noticed that there's a relationship between the resistance and how much of the potential difference they get. In fact, this one is probably not 0.03 volts, it's probably 0.027-ish, something like that. All right, that is for a reason, and we'll talk about that later when we actually get to it. Okay, but let's keep going. We need to look at the parallel setup. Okay, so I've got one here. I've got 100 ohm and 1000 ohm here. So I'm going to draw this out. We've got the following. I've got a battery, just like this. And then I've got a 100 ohm and a 1000 ohm. So 100 ohm and 1000 ohm. Okay. Now the big difference is the ones that we looked at just a moment ago were in series. Now we're in parallel. Let's see what we come up with. So here's what I'm going to do. I'm going to attach one here and one here. And that's going to get us these in parallel. Enjoying sitting on my notes, Cat? Cat has come to visit me. All right, 3 volts. Here we go. So I powered this on. Let's go ahead and double check our potential difference. It's probably not 3 volts. It's probably 2.97. Now, I don't know, that may actually mean that my meter is off slightly. I've had this one for years. It's done pretty well, but it's getting us pretty good measurements. Or that this may be slightly off. I've had these power supplies for a couple years too. But we know that it's delivering about 3 volts. Great. Here we go. So what I'm going to do is I'm going to check the potential difference across the 1000 ohm. Got about 2.93. Okay. Delta V equals 2.93. Great. If I try it on the outside edges here, it's actually, well, it's about 2.93. Okay, great. If I try it here on the 100 ohm, well, that's weird. The 100 ohm is also 2.93. Got something a little different. My total was about 2.97 volts. It looks like this one's pretty much matching the full battery, and this one's pretty much matching the full battery. These don't add together to 2.97 at all. And that's why I wanted you to be careful with the series only, because it may lead you to a wrong conclusion. We need to understand what's going on here. I've got an idea. Let's try one additional thing. Let's set up, I'm not going to put a 10 ohm in there because I don't want to damage my equipment. Let's set up the following. I'm going to add one more branch. I'm going to draw it way out here because I've poorly set this up. That's okay. This is going to be 10,000 ohms. Great. Let's see what we come up with on this. Now, this is on the outside edge, and instead I'm putting it in the middle, but as we talked about, that isn't going to make much of a difference. I can put it over here or over here. As long as they're in parallel with one another, it doesn't actually matter where exactly I put them, as long as they are in parallel, which these are. All right, here we go. So let's see what happens to our 100 ohm. 2.93. My 1000 ohm, 2.93. And my 10,000 ohm, 2.93. Well, that's weird. Why are they all 2.93? All right, let's try one other thing real quick so that we can try and get to the heart of this. These are with parallel. Let's switch this out just a little bit. Okay, here we go. I'm going to do the following. I'm going to add a little bit more on here. Let's see. Where's one of my 5,100? Oh, I think I put my one good 5,100 in another circuit that we're going to take a look at here in just a minute. I don't want to use that. 100 ohm sounds fine. All right, so here's what I'm going to do. I'm going to put 100 ohm here, and then I'm going to do the following. I need some 3s. There's a 3. There are a couple of other 3s. Great. I really do like these snap circuits because building these things by trying to move around real resistors, even in a breadboard, is going to be a bit of a pain and is hard to see. So here's what I'm going to do. I'm going to get this hooked back up, and now we've got some parallel, and one side is in series. So let's see what we got. Here we go. I'm going to, oops. Helps if I hook up the right stuff. Get with the program. All right, here we go. Okay. Power on. Let's see if our supply has changed any. 2.97, so we're still at 2.97. So here we go. The 1,000 ohm, 2.94. The 10,000, 2.94. And the 100s, let's see, so I'm going to check the first 100. Whoa, 1.47. And the other one's 1.47. Okay, let me draw this out real quick just so we can see it clearly, because that's a bit of a change. Okay, so let's see. I've got my battery here. I got one branch that comes down like this, and that's my 1,000 ohm. Another one that comes over here, that's my 10,000 ohm. And then one over here, which is 100 and 100. Okay, great. So what I found was this. This was 2.94. This one was 2.94. The total battery was about 2.97, which is what we keep getting. And then this was 1.47, and this was 1.47. If I add these two together, they'll actually add up to, wait for it, 2.94. Huh. Now I will say something about this. The 2.97, it's giving the same value as the 2.94s. Why it's a little bit off is we've got a little bit of components in here that are actually going to be knocking a few things downhill. Wires have a little bit of resistance, though they're very small compared to the other things that we've got here. Watch what happens when I do the following. So I've got positive 2.97, then I'm going to point out that we're going to call this negative 2.94. Positive 2.97, 2.94, and then they get back to the battery. And then over here, this would also go down 2.94. Batteries give energy, resistors take energy. Now, I keep talking about energy, but I'll remind you that these are all in volts, which are not actually units of energy. They're related to energy, but they're not energy itself, which is one of the things you want to keep in mind, because you may be thinking, well, does this violate conservation of energy? It does not. All right, so I'm going to power this up. Here we go. Let's double check our potential source. 2.97 like usual. 2.93 across the 1,000. Let's try the 100 here. 2.93, and then across the 10,000, 2.9, and across this 100, 0.03. 2.9 plus 0.03 is 2.93, the same as the others. For some reason, each of these branches has the same potential drop. All right, let's try one more, and then we'll discuss what we're actually seeing. All right, here we go. Oh, helps if I actually connect this. I was like, I'm getting 0 reading. Okay, I'm going to check this one. 2.94, 2.94, 1.47, and 1.47. Oh, I accidentally put it back to the first one that we did. Anyway. Here's the thing, and this is why I keep mentioning that it's a height. We're going to compare this in the next video that we take a look at, but I want you to imagine this. The battery is giving these charges energy by lifting them up higher, putting them uphill. They're lifting them up. I told you to imagine the potential difference as a height. It takes it from 0 on one end of the battery up to a height of about 3 volts. Now, they can go one of many different ways. If they go this way, the resistor will let them roll downhill, releasing energy that the resistor will use, and then they'll get back over here to the battery, back at a height of 0. So it goes up 3, and it has to roll down some height when it goes through here, releasing energy. Well, if it ends up back where it started, if it goes up 3, it will go down 3. That's what's happening here. They are heights, and that's why it's not energy. It's not 3 joules, because then we'd end up with 3 here, and 3 here. We'd be making more energy. What this is are heights. This lifts us up by 3, and this drops us down by 3. This drops us down by 3. And these collectively, because they start at the top of the hill and go to the bottom of the hill, they together must be a height of 3. Now, you're going to see that with each of the ones that we set up. That's why they keep adding up to it. Now, we call this Kirchhoff's loop rule. And the reason it's called loop rule is because it applies only in closed loops. We're going to apply that a little bit more when we talk about it more. But let's check this on one other circuit, a big one. I've got this one sitting over here, ready for us. All right, so we're going to do 3 volts across this. I will draw out my circuit diagram. The nice thing about loop rule is it allows us to take incredibly complex circuits and be able to tell a lot of information about one small part of it. Okay, so I've got the following. I've got a battery like this. It goes over to a resistor that then goes over like this. This is pretty similar to the last one that we looked at in the equivalent resistance video. So there we go. Okay. We've got a total potential difference of about 3 volts. We're looking at probably 2.97, just like we did before. And I've got the following. I've got a 100 ohm. I've got a 1000 ohm. I've got a 100 ohm. I've got a 100 ohm here, and then a 5100 ohm resistor here. All right, let's see what we get. All right, here we go. I'm going to check the total. About 2.97 when I get a good read on it. Okay, here we go. Let's see if I've got this hooked up right. I don't. That's okay. Negative. Let me see. I'm trying to get a clear measurement. 1.56. 1.56 volts. Great. Let's check this one. 1.4 volts. Let's try this one. 1.4 volts. Finally, let's check these two. This one, 0.03. Finally, this one, 1.37. Now, I told you, as a heads up, that this is called loop rule. And it applies only in a closed loop. So I'm going to start here on the far side of the battery. I go across the battery, and it raises us up by 3 volts. We go across this resistor, and that brings us down by 1.56, which leaves us with about 1.4 volts left. Remember, this is actually 2.97. So we're right at about 1.4 volts. So we go up 3, we come back down 1.56, and that'll leave us at a height of about 1.43 or 44-ish. And when I go along this brings us down the additional height, which gets us back to 0 where we started. This is one loop. Okay, camera got me again. I got to keep an eye on that. But with these being longer, a lot of information, then the videos are going to go a little bit longer. Okay, so where this left off, we're going around, we were establishing what this is. It is called loop rule, Kirchhoff's loop rule, and we're going to do more with that in the next video, explaining more about it. In short, what it means is in any closed loop, in fact, the way that we usually write it, I just erased it, but Kirchhoff's loop rule says that the sum of the potentials, when you add all of them up as you go around a closed loop in a circuit, they have to add up to 0. We're going to unpack that a little bit more as we go forward, but I told you to think about this as heights. What the battery does is it raises these charges up some height. So we go across the battery and it gives us 3. It moves the charges from 0 volts up to a height of 3 volts. Batteries give energy, so they're going to give us plus 3 volts. We go over here, we go across this resistor, and resistors take away energy, so we're going to have minus 1.56 volts. Now technically this should be 2.97, and that'll leave us with about 1.4, a little more or less. So we go up 3, we come back down 1.6-ish, and we end up at a height of about 1.4. So we go this way, and let's go this branch in the parallel portion of the circuit. This one brings us down another 1.4, and that gets us set where we don't go through anything else. We come back over here, and we end up where we started. According to loop rule, that means, with this being 1.4, we're going to end up with a total of pretty close to 0 volts. Now, this isn't perfect. Remember that this should actually be 2.97, and then they're going to come up to about 0. We've also got that somewhere in here in these wires, we're going to have a little bit of potential loss in there. If instead we followed the green path, we could start here on the far side of the battery, as I like to. We go across the battery. It raises us up to a height of 3 volts. We go across this resistor. It drops us back down by 1.56, taking us to a height of about 1.4. We go through here, through the mid, and this drops us another 1.4, and we end up back where we started. We'll end up with something identical here. Or we could go with the red path, where we start off on the far side of the battery, like I like. We go across the battery, it raises us up to a height of 3. We go across this, it brings us down to a height of 1.4 by subtracting off 1.56. We go down here and go through this branch. This brings us down by 0.03, and then we finish it up with 1.37. We end up back at 0, just the way the other ones did. I cannot emphasize this enough because it's the common thing that people mess up on. It is called loop rule. When you are applying this tool onto circuits, it only applies if you are dealing with a closed loop through your circuit. One of the nice things about this is each of the loops is actually independent of anything else. I could have 1,000 different pieces of this circuit, and all I really have to care about is one closed loop, and I know that the potentials have to add up to 0. Where our batteries give energy, give us height, they raise things up, at least usually, and then our resistors will lower us down. One other thing that I will point out, because of the nature of loop rule, since this is 1.56 and this is 3, that means that whatever the branch is here must be the same as the branch here and here. You'll notice that this is 1.4, this is 1.4, and these together add up to 1.4. So when you're dealing with things that are in parallel, whatever the total potential drop is over that parallel branch must be the same potential drop for each of the other branches. That's very useful information, both for my class and for the AP exam. So this is an introduction to loop rule. We're going to go through that more in the next video and then start expanding on this so that we can start seeing how we solve really big circuits.